We can now move to the application input-output interface. So we are going to talk about drivers now. This part of the lecture is basically discussion about why it is challenging for the operating system to interact, to keep track of the different, interact with the different devices, despite the fact that eventually we need drivers to communicate with each specific device. So, as I mentioned in the beginning of this lecture, but also of this course, the operating system needs to abstract away the specific detailed differences between each type of device and just generalize them. So there is a keyboard, there is a mouse, there is the disk, and so on. As you can imagine, the reason why you want to do this is that you cannot maintain an operating system in which you have dedicated code that is specific to interact with specific type of disks or specific keyboards and so on. You need to decouple a bit the abstraction of a certain type of device with the actual implementation and the actual device you are going to use. And this is what you do by using basically drivers. Okay, you create a separation layer between what the operating system sees as a keyboard and what you are actually using as a keyboard and the way you communicate with your actual device. Okay. The point I'm trying to make here is that even in such a case, finding what are the dimensions along which you can categorize the different types of hardware, it's not a trivial task. So this is how it looks like. This is what I just said. So you have the kernel, you have the portion of it, the subsystem that is about managing input-output. And eventually, at the lower level, you will have drivers. From the operating system perspective, these are abstractions of the specific type of device you are trying to communicate with. So you can have one for the mouse, one for the keyboard, then you have the ones for the SCSI drivers, and then you have the actual specific driver that is the one that will take care of the communication with the physical hardware you install, okay, on your machine. So why is it challenging still to characterize the different types of devices you have? Well, you can look here at some aspects you could use to classify them, and you can see that each one of them has different properties along these dimensions. So you can take into account the mode in which they transfer data, if it's individual characters or if it's blocks, the access method, if it's sequential only or if it can be random, the schedule with which you can manage transfers. So whether you can have basically synchronous or asynchronous communication. You have devices that can be shared and devices that cannot be shared. They are dedicated. They can only be used by one process at the time, or one task at a time. They can perform one task at a time. Of course, they have different speeds, and so you have different latency, seek time, for example, if you are using a rotating disk or an SSD, and you can also classify them based on the direction of the input-output, so whether they are only input, only output, or if they can do both things. Okay, so this is just what I just said. This is pretty simple to follow, I think. So let's just have a look at some types of devices along with these dimensions we can use to classify them. So we have devices that communicate using blocks, so block devices. We discussed this when we were talking about file systems. So when you communicate with the disk, you basically exchange blocks, but then you have other devices like the keyboard or the mouse in which you actually have exchanges that are of smaller sizes. They are of individual characters. So you can imagine that the operating system needs to provide different APIs. You can have read, write, and seek for a block device, and you will probably have a get and put that are for sequential ordered interaction with character devices. when you want to share data with a disk or when you're reading data from the keyboard, you can imagine that this is completely different from actually communicating data or getting data to the network. Here you cannot really have a random access, okay, because you can only get the next portion of bytes that you are retrieving to the network, or send the next portion of bytes through the network. Okay, so in that case, the operating system needs a different interface for network devices that it uses for disks, for example. So you can have a read and write API, for example. Then you have completely different types of devices that are clocks and timers. So you will probably need to define APIs that you can use either to keep track of the elapsed time or basically the current time, but also to set triggers when a certain amount of time expires. Okay, and we discussed this for the when we were discussing processing, right? Scheduling. Sorry, you want the operating system to wake up periodically to take scheduling decisions independently of the processes you're running and whether they are going back into ready or waiting state. And to do that, you use specific pieces of hardware that are the clocks of the computers, basically. Then another thing you can think about when you are designing an operating system and you are deciding the way in which you can communicate with, for example, block devices is the type of communication you have. So you can have blocking or non-blocking. Blocking basically means that you can create APIs that will suspend the execution of the process as soon as that process is trying, for example, to write something to disk or read something from the disk or some other device. It's easier to make to go for a blocking API because it's easier to maintain code and also write applications that are blocking. You don't have the problem of defining code that can keep executing despite the fact that it needs some information and needs to be notified when that information is available. Or, for example, when a certain amount of data has been written to disk or it's available from the disk. You can create non-blocking versions of the APIs at the operating system level by having multi-threaded executions in which you transfer the data from the thread that is requesting, let's say, to write something to a different thread, and then you allow this second thread to block. So the operating system can, of course, provide APIs that are non-blocking by maintaining internally its own extra threads and managing the transfer to disks with these threads rather than the specific threads that are executing on the, let's say, the user processes. Then, of course, aside from blocking and non-blocking, you can also have true asynchronous APIs. So in that case, if the hardware supports asynchronous input and output, then you can make a more performant operating system that is also more complicated, of course, to define and to develop, that will use signals and share these signals with the threads of the user processes whenever asynchronous input-output requests have been handled by the hardware.